Hello everybody, welcome back to another Gregorius Maths video. In today's video, we'll be extending the factorial to the positive integers. No, I will not be doing a calculator review in this video or soon, but maybe I'll do a calculator review sometime in the future. Okay, in today's video we'll be introducing the gamma function. Because we're gonna use it in tomorrow's video as well, or my next video, hopefully tomorrow's video. Okay, so we all know that n factorial equals n times n minus 1 times n minus 2 times 2 times 1. Okay? We also know this can be a useful property of the factorials is n factorial equals n times n minus 1 factorial. Yeah. And okay, so these are two useful properties. We also know that 0 factorial equals 1. Okay, so this definition here works, my handwriting's pretty bad, works for all n an element of the natural numbers. Okay? This works for all n an element of the natural numbers, so 1, 2, 3, 4, 5, duh. But now, what do we want? We want a function f such that f of x equals x times f of x minus 1, okay, and f of 0 equal to 1. Okay, this just means that x factorial equals x times x minus 1 factorial, and this just means that 0 factorial is 1. Turns out that the solution is the pi function, pi of x equals the integral between 0 and infinity of t to the power of x times e to the negative t dt. Okay, this is the precise solution. This works for all x which is positive. But for some reason this function here is a pretty irrelevant function compared to the gamma function. Gamma of x equals the integral between 0 and infinity of t to the power of x minus 1 times e to the negative t dt. Okay, so the solution can also be gamma of x plus 1, which equals the pi of x, which equals this integral. Okay, so now we're just going to check that the initial value f of 0 is 1. As an exercise you can check different values, and also you can check that this is true. Okay. So, gamma of 1 equals 0 factorial, which equals the integral between 0 and infinity of t to the power of 0 times e to the negative t dt, which is just, this will always be 1. This can go away. So this equals the integral between 0 and infinity of e to the negative t dt. I'm just going to zoom through this quite quickly. this equals negative e to the negative t evaluated at the bound 0 and infinity, which equals 0 minus minus 1, which equals 1. Okay? You can slow that down if you want to see all the working. I just zoomed through that so that we can get onto the point of this video. Okay, but this is, yeah, this is the working. Okay. So now, our new goal is to solve for 1/2 factorial equals. Okay? Well, let's do this integral. Gamma of 3/2 equals 1/2 factorial, which equals the integral between 0 and infinity of t to the power of 1/2 times e to the negative 2 dt. And now, u sub in blue, let u equal t to the power of 1/2, meaning that u squared equals t, or 2u du equals dut. Now let's plug this in. The integral from, well, when t equals 0, u is also equal to 0, so u equals 0. And then when t equals infinity, the square of infinity is just infinity. I forgot to do this in my last video when I did a u sub. You always have to check that u equals t at the bounds, because, say for example this was the integral from -1 to infinity, then in the u world this would be the integral from I to infinity. So we always have to check. So u times e to the negative u squared times 2 times u du. Okay, let's clean this up. This equals 2 is just a constant, we can bring that to the front. 0 to infinity of u times e to the negative u squared. The reason I didn't write this out as u squared is because actually what we want this part, because we know how to integrate this. We know the solution to this integral. And then we can just do an integration by parts. So, di method plus minus u1 u times e to the negative u squared. The integral of this is -1/2 e to the negative u squared. I think you have to do a substitution, but I'll just say, because, well, if we differentiate this, we get -1/2 e to the negative u squared times 2u, times -2u, meaning that this will go away, and this will become positive u, which is exactly what we had here. And now we'll stop. Even though if we differentiate this we'll get 0, we know how to integrate this product. Yeah, so it'll be quite useless because we just want to get this product anyway. Okay, so part of the answer is 2 times that evaluated at the bounds. So 2 times -1/2 u times e to the negative u squared, evaluated from 0 to infinity, and then minus becomes plus, 1 times this, so the product of a row is always an integral. The integral between 0 and infinity of, oh yeah, and also distribute the 2, so 2 times 1/2 e to the negative u squared. So what I did here, distributing the 2, bringing the half to the outside, and the negative and the negative become positive. So, first of all, let's get rid of this. So this equals, okay, negative u e to the negative u squared evaluated at the bounds 0 and infinity, plus that will cancel the integral between 0 and infinity of e to the negative u squared. First of all, let's look at this. Well, when we plug in infinity into here, this just goes straight down to 0. So equals 0 minus. And when we plug in 0 into here, this also becomes 0. So 0 minus 0, looks like glasses on castling if you play chess. Plus the integral between 0 and infinity of e to the negative u squared. Oh, du, which equals, and for my more loyal fans who actually watched my last video, you'll recognise this integral. This looks like the Gaussian integral which I evaluated yesterday, except from 0 to infinity, not negative infinity to infinity. And therefore, because it's a symmetrical function, e to the negative u squared, this is exactly half of that integral, or square root of pi divided by 2. And so, that's tiring. Okay. Basically, 1/2 factorial equals square root of pi divided by 2. Okay. Thank you guys for watching. Hopefully you enjoyed the video, and I'll see you in my next one. Goodbye.